nanohub.org.
Online simulation and more for nanotechnology.
Okay, good morning. I will discuss multiscale modeling of graphene metal contacts. This is an activity that we have done at the University of Pisa within a couple of European projects in which we are participating. Let's start with the motivation. Well, metal graphene contacts are a critical aspect for the performance of graphene transistors. You see this picture here. It shows the output characteristics of graphene FET. It's fabricated recently at IBM. These output characteristics are very poor, actually, and the reason is that the series resistance of the contacts is too high. And this undermines, of course, both the achievable voltage gain of the device and, for example, the high frequency performance, the Fmax in particular. We also need to fully understand what happens in metal graphene contacts, also because we cannot rely that much on experiments. Results in the literature are very much scattered over various factors in terms of obtained results, also because some relevant factors are not fully controlled in experiments. So what we do about it? We simulate with ab initio atomistic DFT simulations using quantum espresso structures such as this. We have two metal regions connected by a graphene sheet. We use a plane wave basis set and a gradient corrected PBE exchange correlation functional. The structure is symmetric because we want to avoid artificially induced dipoles in the structure. We consider 4 different types of metal. 2 are chemisorbed on graphene, so they form a strong bond. They are nickel and palladium. And 2 are physisorbed, so they form a weaker bond, particular copper and platinum. And we, let's say, in a simplified way, we optimize the geometry, we optimize the distance between the metal layer and the graphene sheet. So we also consider more than one geometry, in particular the first 2 here. We call it the first a long structure and the second a short structure. The only difference is the separation between the 2 metal regions. And we will show that this has relevance. Now, how do we proceed? First, we solve the electrostatics, basically, with quantum espresso, and then we attack the transport problem. What do? We cut the graphene layer at a certain point, in one of the points shown in the figure. For example, here, we put a semi-infinite graphene lead on the left side and a semi-infinite metal lead on the right side, and then we can solve the scattering problem considering ingoing and outgoing block wave functions. This thing is done within quantum espresso by a specific module which is called PWCond. So by using it, we can, of course, compute the transmission coefficient as a function of energy, and from it we can obtain the conductance. This is a very simple procedure in principle, and this is what we obtain. You see, the transmission coefficient as a function of energy, and the different curves are for different cut points of graphene, so different points of insertion of the semi-infinite graphene lead. You see that the curves are very different. If we want to compute the conductance, we need to, according to the Landau formula, integrate the transmission coefficient around 0, around the Fermi energy. And of course, you see that the result will depend a lot on which curve we choose, which means on where we cut. And this is an important observation because the resistance of the metal graphene contacts actually depends a lot on the graphene region between the 2 metal regions, on the extension of the graphene region. Okay? And this is something that in experiments is not sufficiently considered, is not totally controlled. Now, why is that exactly? Well, it is also easy to see. Look at this picture above. It's a simplified picture of the structure. We basically have the two blue regions that are the metal regions, and the arc in the middle represents the profile of the Dirac point in graphene between one metal region to the other. So basically, when we compute the transmission, we, for example, make a cut in the middle and insert a semi-infinite lead. And of course, if you compute the transmission of this structure at the energy corresponding to the energy of the Dirac point in the semi-infinite lead, you will have to have zero transmission, because for that energy, the density of states of the semi-infinite graphene lead is zero. And this is what we have here. The transmission coefficient goes to zero. For example, the situation that I've illustrated above corresponds to this red line for the long structure. The transmission coefficient is zero at an energy below zero. When we move the cut point towards the metal, of course, we have the zero transmission at the lower energy, so the whole curves shift to the left. To the right, to the left for you, of course, and to the right for me. Okay, this is what is happening here. So, the interpretation is easy. Let us look at the literature. So, in this table, we have different rows corresponding to different metals for the contact. The first two rows correspond to the computed resistance for the long structure and for the short structure. And you can see there is a large difference, a factor 3 between the long structure and the short structure. The graphene region between the two metal regions is about between 1 and 2 nanometers. It's very, very small. And the last two columns correspond to results from the literature in experiments and in simulations. You see, the results are pretty much scattered, but of course we can say that with simulations we are in the ballpark of the experimental results. By adjusting the distance between the two metal regions, we are easily in the ballpark of the results that are obtained in experiments, except for palladium, basically. For palladium, we think that in practice we do not have the proper geometry. Something is happening that we do not reproduce in the model. Probably we're thinking now about the formation of carbides at the interface. So, why is that? Why there is such a difference? Because if we just consider the ballistic resistance of an infinite graphene sheet, it varies a lot as a function of the energy of the Dirac point. It can go up to more than 300 ohm per micron, which is a lot, to something much smaller. Of course, for a good contact, we need something which is smaller than 100 ohm per micron, so we need to be in this range on the right. And to be in this range, we of course need to push the energy of the Dirac point far away from the Fermi energy. Okay, then let us consider again the data that we have obtained to understand something more in terms of a simpler model to describe the contacts. So this pink region here represents the short structure. Let's look at that. The rows correspond to different species of metal for the contacts. The first column is the resistance of the structure of the contact from metal to metal that we have already shown before. The second column is the energy of the Dirac point at the cut point, in the point in which we introduce the semi-infinite lead. The third column is the ballistic resistance of the graphene lead that we introduce. And finally, the fourth column is the ratio of the ballistic resistance of the graphene lead to the contact resistance. Okay? And we do the same thing for the long structure. You know, the numbers are very much different, but there are some things that do not change. And in particular, these ratio columns are basically the same for the long structure and for the short structure. So we can interpret them as something that intrinsically depends on the nature of the interface between the metal and graphene. We interpret it as an effective transmission coefficient of the interface at the Fermi energy. And once we do this observation, we can do something even simpler. We can build a two-parameter contact model, which is very easy and captures all the relevant physics. One parameter is this effective transmission coefficient at the contact, and the other parameter is just the energy of the Dirac point at the metal interface that we call delta EF contact. With these two parameters, we can basically include the contact in device simulations, either in NEGF simulations or in also semi-classical simulations. And we also have a recipe for how to improve the conductance of the contact. Because, for example, what can we do if we need to fabricate a GFET? We have this yellow region, which is an insulating layer, then we put a graphene layer on top, two metal regions, and a top dielectric. Then we put a top gate, and the figure below shows what happens at the contact. We have the metal region, the Dirac point at the interface with the contact, and then the energy of the Dirac point in the space of less than 1 nanometers goes much closer to the Fermi energy. If we want to improve the conductance of the contact, we just need to put a back gate below and to apply a positive gate, a positive voltage on the back gate. If we do that, we can push down the energy of the Dirac point and therefore improve the contact resistance. It's very easy. If we can also evaluate what is the achievable minimum resistance, because we know for the different metals the energy of the Dirac point, we know the effective transmission at the interface, we know now the ballistic resistance of graphene when we have a flat potential in the graphene layer, and therefore we can, let's say, divide this ballistic resistance by the transmission coefficient at the interface and obtain the minimum contact resistance. These numbers are around a few hundred ohms, except for nickel, which is actually very interesting because it's 30 ohm per micron. That would be very good for transistor contact resistance. So, with this I can conclude. Basically, we have performed ab initio atomistic simulations of metal graphene contacts with quantum espresso. We have derived a simple model for the contacts based on only two parameters that capture all the relevant physics of the contact. It can be easily introduced in a device-level simulator based on NEGF. And according to this model, we have been able to predict a minimum achievable resistance in the case of nickel graphene contacts of about 30 ohm per micron. Thank you for your attention.